Okay, so we've been gone a while, right? I mean, it's been, if we think about, we had SBAC, we were reviewing for 4 days before SBAC, we had SBAC testing last week. So it's been a long time. So I want to kind of put things in perspective a little bit before we jump into stuff. Here's where we are, right? Where we left off, kind of think back, and this has been like 2 weeks ago, right? Think where we were though. In Unit 5, we're talking about polynomials. All right, we spent some time, at the beginning we spent some time just learning what a polynomial was. But then we added and subtracted and multiplied and divided polynomials. We divided using long division and synthetic division. And then we moved on and we started to focus on solving polynomial equations, which is a pretty big topic, right? So let's kind of get our bearings here. Remember what we said. We're going to look at, in Algebra 2, we're essentially going to look at 3 different types of polynomial equations. And it's easy to keep the strategies straight because they're easy to identify which is which. We're going to look at polynomials with 2 terms, polynomials with 3 terms, and polynomials with 4 terms, right? And where we were before we did our big interruption, we were focusing on polynomials with 2 terms. And what we're going to do today, I want to review that a little bit today. It's been, because it's been a while. So we'll spend a little time reviewing that. That sort of naturally leads into the next category, which would be polynomials with 3 terms. And we'll introduce that today. We'll get through maybe an example or 2. I've got an assignment up for you. And then in the near future, next few days, we'll look at the last case, which is polynomials with 4 terms. Now, 4 terms, this is something completely new to you. It's not difficult, but when we get there, I'll be introducing something completely new. But I want you to keep in the back of your mind, as we start the second category today, polynomials with 3 terms, this is something that's going to be really easy because it's essentially stuff we've already done all year. It's just a slightly different context or application, but it's stuff that you'd be very familiar to, okay? All right, so that's kind of where we are. Let's do a little review. So, binomial factoring patterns. When we're solving polynomials with 2 terms, the way we did this, you might remember, is with binomial factoring patterns. And so this is just the slide that we looked at 2 weeks ago, right? Let's take a quick look at this and kind of refresh our memories, and then we'll launch into a couple examples. So remember that now we're going to limit ourselves to binomial factoring patterns where we've got terms that are being squared or terms that are being cubed. And that's it. We're not going to do anything more complex than that. So that leaves us with 4 possible patterns. The polynomial looks like something squared plus something squared, which we call a sum of squares. It looks like something squared minus something squared, which would be a difference of squares. Something cubed minus something cubed would be a difference of cubes, we call that. Or something cubed plus something cubed, we call a sum of cubes. And in these patterns, the A and the B just represent somethings. They could be x's, they could be numbers. In our polynomials, they're not going to look like a's and b's, right? These are the general patterns we're going to use. And so let's refresh our memories here. Well, the good news is a sum of squares pattern is there's no pattern. If you see something that looks like something squared plus something squared, the good news is there's nothing to do in terms of factoring. You can't do anything. It doesn't factor. If we have a difference of squares, remember that works out to be the conjugate pattern. So a squared minus b squared is going to factor into a plus b times a minus b. And that one should be pretty familiar. We looked at that kind of in reverse order last unit. But the cube ones were very different, right? And they're a little bit hard to remember. I know I keep dropping the ball on this. I told you we're going to do this soon. I wish I would have done it a little bit sooner, but I'll give you the paper tomorrow. I promise you, I'll give you the paper tomorrow. We're going to do our little memorization test over this stuff. It helps. It's kind of a hindrance when you're trying to learn math, and you have to always stop and look up what the pattern is, right? It's just a lot easier, and there aren't very many cases like this, in my opinion. I don't like to waste a lot of brain cells memorizing things. It's kind of low-level learning, but in this case, we want to have a working knowledge of these patterns. And so I'm going to give you the sheet tomorrow with a summary of all the sum and difference factoring patterns. We'll add the expansion patterns on there. And let's just say next Wednesday. We'll set the date. Next Wednesday we'll do a little memorization quiz over all that stuff. So it kind of forces you to internalize it. You got to memorize it. If you need index cards, I can get index cards. That's the greatest way in the world to learn facts. Is just put the question on one side and the answer on the other side. So on your index card, if you go that route, on one side it's going to say a cubed minus b cubed, and on the other side it's going to say the factoring pattern, right?
Is it also going to be the cubes?
And then, right, and we'll get our perfect squares up through 15 and our perfect cubes up through 10. And I'll give you all that on a piece of paper tomorrow, so it's all in one place. There's your memorization study guide. Great deal. You get a Algebra 2 test grade for memorizing some stuff. That's a pretty good deal. You don't get that very often, so, enjoy it while it lasts. What's our pattern, though? Okay, so let's look at ways that we can kind of remember how this pattern works. Whenever I'm going to break down either a difference of cubes or a sum of cubes into its factored form, I want to factor that into pieces. Remember, we talked about this a while ago. We can always break it down into a small factor, a binomial with 2 terms, and then a big factor, a trinomial with 3 terms. The terms that show up in the binomial are always going to be the first term is an A and the second term is a B. So we're just looking at the white parts of this pattern right now. Ignore the signs for a second. So we get an A and a B. In the trinomial, we're going to get an A squared for our first term, then the product of A and B for our middle term, and then a B squared for our last term. All you got to remember is, once you can remember what the pieces are, what the terms are in each factor, is what signs go where. And here's how we remember that. If it's a difference of cubes, so a cubed minus b cubed, then the sign that goes between the a and the b is a minus. It's always going to be, if it's an a cubed plus b cubed, it's an a plus b. It's always the same as whatever the operation is separating the a cubed and the b cubed, right? The first sign, so the next sign, which would be the first sign in the trinomial, is always going to flip. If that's minus, that's plus. If that's plus, that's minus. And then the last one, remember, is always going to end up being plus b squared. Okay? So those are our patterns. Something else that we mentioned, when we factor using the sum and difference of cubes, the trinomial that we get is always going to be an irreducible factor. So you're not ever going to be able to factor that any further, so don't even waste your time trying. And we'll look at some examples today where that'll come up. If we are solving an equation by factoring and we set this one equal to 0, the other thing you can always remember is we're always going to get imaginary zeros. We're never going to be real zeros. Okay? All right, so let's launch in and let's look at an example. Well, first of all, just a little warm-up. Just a quick little warm-up. So this goes clear back to Unit 2. If I want to solve this quadratic equation, what am I probably going to do here? Okay, we want to go through our checklist, right? Can I isolate x here? No, I can't. I can't point to a single x. I've got x squareds and x's, so unfortunately that would be the best option, but it doesn't work this time. What's our next option? Magic numbers. Good, factor it. So what can we find magic numbers? What would they have to multiply to? Negative 12, okay. And they'd have to add to negative 1, okay. So can we find magic numbers that do that?
3 negative 4.
3 and negative 4. There you go, perfect. Yeah, so x plus 3, x minus 4. Okay, why did we do it though? We haven't talked about the why in a while, but why are we factoring this thing? How does that help us?
It's a single x.
Okay, we were able to break it down. Instead of one big equation with an x squared, I get these 2 factors. And what do we call the property that we use to?
Zero product property.
The zero product property, right? Remember that the product of factors can only equal 0 when you're multiplying by 0, right? So the only way that the product of x plus 3 and x minus 4 could possibly equal 0 is if either x plus 3 equals 0 or x minus 4 equals 0. Good. And so that gives us the solutions x equals. Okay. So point being that by factoring stuff, that's an easy problem, but let's reflect on why we're doing it for a second. We're doing it this way because we're trading a big function for small factors, which are easy to set equal to 0 and solve, right? Okay, so the same approach we're going to take with something like this. Okay? So this is, it looks like a mess right now, but what do we always do with any equation? What's the first step we're always going to take? Okay, I've heard a bunch, to my like terms, I heard a bunch of different ways of saying the same thing, set it equal to 0, put it in standard form, it's all the same thing, right? We want to get everything on one side equal to 0. How do we do that in this case?
Add news.
Add, what do you mean add 7? Add 7. Okay, so we end up with 0 on the right side, which is what we want. The 7's cancel. And I end up with negative 54 x to the 5th plus 128, running out of room, plus 128 x squared equals 0. Good. Step number 1, we got it in standard form. Always our starting place. Yes, sir.
Multiply the left side by -1 or left side by -1.
Okay, sure, we could do that too. Good. So we'd like to have a positive coefficient, so we could multiply both sides by -1. That's fine, we can do that. If I multiply both sides of an equation by -1, what does it do to a polynomial? What's it do to all the terms? Flips them, flips the sides. Okay, so we end up with positive 54 x to the 5th minus 128 x squared equals 0. Very good. Okay, so now what? What's something else that we always want to try to do? It doesn't always work, but what do we always want to try to do?
Factor out from the coefficient.
Okay, greatest common factor. See what's the greatest common factor, meaning what's the biggest thing we could undistribute, right? So we want to look at that in terms of what's the biggest number we could undistribute, and then can we take any variables with it, right? So let's see, what is the biggest number that goes into both of those?
Is it 9?
I'm gonna say 9.
6. Well, okay, now hold on. 128. What's our
Add them
little,
up.
this is like a,
Add
I
all
don't know when
three
you first
numbers
learned
up.
this. Okay, if I add the numbers up, 1 plus 2 plus 8 is 11.
No.
Is 11 divisible by 3? No,
it's
so
not
if
divisible
3 doesn't
by
go
9.
into it, obviously 9 can't go into it, right? So we can't divide 3. Let's start small. Is there something that can go into both? 2. Okay, so I could factor out a 2, right? Can I take any variables with it?
X squared.
I can take an x squared. Good, I've got an x to the 5th here, but only an x squared, so I can undistribute an x squared. And if I do that, let's figure out, oops.
Big oop, Mr. William.
I know it. I do that all the time, don't I? It's just a comedy errors up there. So, you said we're gonna factor out a 2x, and we wanna figure out what's left behind.
2x squared.
2x squared, good. 2x squared. If I want to figure out what's left behind, now remember, if I want to figure out what's left behind, I could ask myself 2x squared times what is that, right? It's 54x to the 5th. But you can always, when we get bigger GCFs, greatest common factors, we can also do this. I can just divide by 2x squared to see what's left behind. There we go. So 54 over 2, there's my 27, good. And I heard it, x to the 5th over x squared is
X cubed.
x cubed. Okay. And then how about here? If I divide by 2x squared,
Negative 64.
good, 64. And then the x squares would cancel, right? Okay? Good. Okay, we're getting there. Well, that's progress, right? Because now we got it to a point where I've got it factored. At least it's a little better than it was initially, right? In fact, if I wanted to, this first factor I can already deal with, right? If I took that first factor and I set it equal to 0, by the zero product property, what would my solution be?
0.
0, yeah. Only value of x that would make 2x squared equals 0 is 0. So there's one solution right there. We already know one answer, right? But I don't know the others. Now, it's a 5th degree polynomial. See if you remember this. How many complex
5.
solutions should it have? 5, right? It should have 5 total, but remember that because the x is being squared here, it actually counts as 2, right? But we know we've got more to come. We've got 3 more to go. Where are they going to come from?
The x squared, not cubed.
Okay, from this one, right? But if I set this equal to 0 right now and try to solve, I can't do it, right? Because I don't know how, there is no magic silver bullet to solve for a cubic. There's no cubic equation. Now, we have a quadratic equation we can always use, a quadratic formula we can use, right? But there is no cubic formula. So I've got to do something with this. I've got to break it down further. So here I've got this polynomial that's got two terms. What's our strategy for a two-term polynomial? Factor it more, and how do we do that? I don't remember. How does that work?
May I suggest a sum difference?
Okay, we might suggest maybe a sum or difference pattern, but we just got to figure out which one. So if we look at this two-term polynomial, well, first of all, is it a sum or a difference? It's a difference, so we know it's going to be a difference. Which one of these, and really you want to look at the exponents here. Which one of those is the one that's going to work? A difference of squares or a difference of cubes? It's got to be a cube because I've got an x cubed, right? So the pattern we want then for this guy is a cubed minus b cubed. And so the first step is let's remember what the formula is. I want
A plus
yeah,
A plus B.
so I get a small factor times a big factor. What's the first? What are the terms in this one? A and B. Okay, William, what are the terms in this one right here?
A squared.
William, a squared.
B squared.
B squared goes there. What goes in the middle?
AB.
AB. Okay, what about my signs?
Negative.
Minus.
Plus. Negative.
Minus plus.
Positive. The last one's always positive. Good. Okay? So there's my factoring pattern. Now the question is just, can I figure out what my A and my B are, right? So my goal is I want to take my 27x cubed minus 64, and I want to see if there's a way that I could write that as something cubed minus something cubed, a difference of cubes, right? Okay, well, the second something is probably the easiest. What cubed is 64? 4. Okay? So my B is equal to 4, right? Now the first one's a little tougher. What cubed is going to give me 27x cubed? Okay, so I need a 3 because 3 cubed is 27, and then I need an x because x cubed is x cubed, right? So A is equal to 3x. So I want to break this up into its factored form, and so here's the template we're going to use, right? We're just going to, it's going to be this answer, but we have to insert our A's and B's, right? So what's that give us then?
Sorry, wait, Emily's doing,
Okay.
someone got in a fight.
Oh, I
I
gotcha.
can't find, well, I saw her, but she said, wait 1 moment.
Okay,
Now it turned into like half this period.
I gotcha. Here,
You
give
don't
it.
need, you can just put it in, I guess.
Oh, that'll work. You going right down there?
Exactly.
Okay. All right, there you go.
Thank you.
You're good. All right, so okay, so what's our A?
3x.
Okay, so then I end up, instead of A minus B, I'm going to get 3x minus 4. Okay, good. That looks good. We can deal with that factor, right?
3x.
Okay, now we got to be careful. Ooh, this is the one that's tough, though. This is the one, if you're going to make a mistake, this is where.
The whole world should go around. She's like, oh. You know when it was kill?
It's test 2, by the way.
Hang on. Hang on. 1 sec. Hold that thought, folks. Hold that thought.
Are we quitting this, Mr. Williams?
What's that? I know. That's all right. Lots of things get recorded.
She's too good for that.
Mr. Haig would change it on.
That's nice.
There you go. You're good. All right.
Thank you.
You bet. Okay, back to business. Okay, so here we go. Here we go. So we got our first factor. A minus B became 3x minus 4. Now the second one. Here's where we got to be. Okay, you're already stepping
I'm
ahead
a
of me.
genius, Mr. Hoya.
You are, I agree. So A squared, A you told me is 3x, so I got to square the whole 3x. What's that going to give me?
9x squared.
Good, I got to square the 3 and the x. Very good. So we're going to get a 9x squared plus A times B. Well, what's that? A times B. 12x. Very good. And then B squared would be 16. Okay, good. So then we broke apart, look what we did, we took this difference of cubes and we broke it up into smaller, manageable factors. The first one is linear, that's an easy one to solve, isn't it? So let's write this whole thing out in factored form, just for a second. We want to keep track of where we are. So we've got our original function, we broke it down to here, right? And then we went one step further and we split apart the difference of cubes. And now we can write it as 2x squared times the green broke apart into two parts. Whoops, that's the wrong color. Broke apart into 3x minus 4 times 9x squared plus 12x plus 16. And remember, our whole goal is we're trying to solve an equation. And it's all equal to 0. So now we've got it far enough that we can apply the zero product property, right? I'm going to go to the next page. I've run out of room.
Why do you choose the background doing black?
You know,
Yeah.
I used to do
Okay,
it white,
Mr. Oya.
but then I like the way Khan Academy did it, and people have all told me they like it better this way. Are
It's on
you?
night mode.
It's kind of like night mode, you're right.
You use night mode when you're on Twitter?
I didn't go on Twitter, so I wouldn't know.
That was good.
Okay, so now look where we are. So we got this thing broken up into small enough factors. Notice that each one of those factors is either quadratic or smaller. So if I set them equal to 0, I'm going to get equations I can deal with. The worst case scenario is a quadratic equation. We already did this one, and we found that x is 0. Let's deal with these. If I set this guy equal to 0, whoops. What are the two steps to solve for x?
Add 4 and then divide by 3.
Add 4, divide by 3. So what's that going to give me?
3/4. So negative 4/3.
4/3.
Four
Okay,
thirds.
there we go. 4/3. There's another solution. Okay. Now, what did we say about this one? This is the bigger one, the trinomial part of our.
Quadratic formula.
Okay, I'm going to have to use quadratic formula, but what kind of answer should we always expect to get?
Imaginary.
Okay, imaginary. Okay, let's watch that happen. All right, if I set this one equal to 0. If I set that equal to 0, I'm going to have to use the quadratic formula, right? Okay, so real quick, there's the equation we're solving. So quadratic formula, it's been a while, let's warm up your singing voices. So if I've got a quadratic equation in standard form, ax squared plus bx plus c equals 0, how's that go? X
This is a
equals
nice
Brody, you're not singing?
b squared minus 4ac divided by 2a. That was beautiful. Thing of beauty. Okay, so all we got to do then is we've just got to identify what A, B, and C are for us, and then plug and chug, right? So what are we going to get then? So I'm going to get x equals, what's B for us?
Negative 12.
So B is 12. I'm going to get negative 12. Good. There's my B. Plus or minus the square root of B squared. So that's going to be a 12 squared. Good. Minus 4 times 9. There's my A times C, which is 16. Very good. All divided by
2 times
9, which is 18. Very good. Okay, so then we just have to simplify that. Now there's a little bit of work involved, but it's repetitive. Once you do this a few times, get back in the swing of things, you got it. So remember, when we're simplifying answers with the quadratic formula, we want to break it up we want to split the denominator into two different fractions. So we're going to get negative 12/18 plus or minus, there's my plus or minus, the square root of all this stuff. Now let's see if we can do that. So 12 squared is what?
144.
Okay, minus, here's how I would do this one. 9 times 16?
No idea.
What was it? Did you get it, Regina? Something, you're right, it's something.
9 times 8 twice.
64.
There you go.
154.
9 times 8 is
72.
72 times 2?
142.
144.
100, that's such a a great technique, but someone finished the job for us. 72 times 2 is 144.
It's okay, I quit easily.
Times 4.
Negative
Times 4. If we multiply by 4, we double and redouble. So
It's
did that make
negative
it
four.
Times negative 4.
That's okay. It's negative 4. So we've got a 4. At this point, we've got 4 times
288 plus
144. So we double and we get 288. We double again and get
1,624.
400. 576. Okay.
Numbers.
Okay,
It's gonna be
and
imaginary.
hey, do this. This is the kind. I'm not kidding. This is the kind of stuff. If you look at brain science, the very same parts of your brain are active when you do mental math. They're active when you do algebra. It's the same patterns of thought. So 144
So there could be imaginary
minus
numbers.
576 over 18.
So there's gonna be imaginary numbers.
We but we knew that, right?
Yeah.
We knew that. We're going to get eyes in this. So 144 minus 576. That one just
Yeah, but
happens
we'll
to be
432.
432. What do you know? Okay. So we end up with. Oh my goodness! Why is it doing this to me today? It's the glitch.
It's a virus. What are you watching, Mr. Oya?
Oh, Jaden.
What's going on?
Okay, bro, what's wrong with it?
I'm talking about
No, it kind of leaked out of me. So what is 12/18 reduced to?
Negative 2/3.
I would have gone there eventually.
Plus or minus? Phone should be way. Oh, you doing calculator work?
Yeah.
Good. Okay. The square root of, we said that was negative 432 divided by 18. So what's going to happen to the negative inside the radical? It's going to be an I. Okay, but we got to simplify the square root of 432. So let's, it's been a while. Let's quickly look at our factor tree. So we got to break it down with a factor tree. Couples go out, singles stay in, right? So 432 we could break up into 108 times 4. 108 we could break up into 27 times 4. And the 27 we could break up into 3 times 9, and then the 9 we could break up into 3 times 3, right?
3 times 4 is...
And so look what we get. We get a couple of 4s, a couple of 3s, and a single 3. So couples go out, so the 4 and the 3 go out, and the single stays in, right? So we should end up with then
12 times the square root of 3. I.
Yeah, good.
12 times the 3.
But, oh, plus or minus, the negative 1 is going to become an I. The 432 is going to become a,
12 times square root of 3.
we said a 4 times a 3, good,
12.
which is 12. I'm just going to write it as, for a second, I'm going to write it as 4 times 3 for the notes, times the square root of, oh my goodness, this has to color coordinate, times the square root
That's your
of
own fault.
3, because that's the single, right?
You make it harder on yourself. Just
All right,
more colors.
but I like to do
It
this for
helps
the,
with the notes.
it helps with the notes, you can follow the notes better.
Yeah, okay.
Come on
Divided
now.
by 18, and we have a negative 2/3 out front. So this is getting better. This is getting better.
Plus or minus 2 times the square root of 3.
So that becomes a 12. 12 over 18 reduces to
2/3.
2/3. So I end up with, I forgot my I. So I get 2 over 3. I got a square root of 3.
Times I.
I got my I. And look what we get here then. So how many solutions are there? 2.
Wait, how come
Let's
you
count 'em
can't-
up.
How come you can't separate the 12 over 8 and then do the square root of 3 over 8? What? Yeah, I said that, yeah.
Okay, so
Like, why is
say that again, because I didn't understand that.
So how, you know, how we're usually supposed to separate the denominators, each one can have its own denominator? Why
Mm-hmm.
is like on the one that's squared, like not like, you know, like you put a box around it over there? How come it's 2 over 3 and then also the
Okay, so
when we split the fraction up, so the 18 is gonna go with the negative 12 and
Yeah.
with all that junk,
So
right?
that has to stay over there.
Right, because this is the plus and this is the plus and minus sign, right? So that's what's separating the two terms. I've got terms are the things that are being added or subtracted. So I've got a term plus a term or a term minus a term on the top, because all this stuff is inside the radical. This is one thing, just one term, okay? Does that make sense?
Yeah.
Okay. So we get two solutions here that have i's in them. I want you to notice something about this, because we're going to come back to this here in about a week. Notice that when we get a pair of solutions that involve an I, notice that they come as a conjugate pair. They come as a term plus a term and the same term minus a term. They always come in pairs like that, right? We talked a little bit about that, but we'll see that a little bit more in a week. So when we solve for x, in the case where we're going to get i's, they always come as a package deal. They come as a complex conjugate pair. Okay, we'll come, like I said, we'll come back. And so, what are our solutions then? Well, we got a 0, we got a real solution, x equals 0, we got x equals 4/3, and then we got a couple of imaginary solutions.
I was
That's
gonna
only,
get 3 though.
4.
It's only 4, but, you're right, it's only 4. But remember, because the x was being squared, it counts as 2. Because there's really two factors there. I get 2 times x times
Oh,
x, right? Okay, question? Did I see a question over here? Yes.
Can you go back to the other page?
Yes. That page?
Yes, go to
Yes.
the bottom.
Okay.
Now, would you be able to just get rid of the 2/3 times square root of 3? Because if you're just multiplying 2 times square root of 3 divided by 3, it's the same as multiplying 2/3 times square root of 3. So would you be able to add or subtract 2/3 just to make it more simpler?
So,
if you just,
is this what you're saying? Could you write that as 2/3 times the square root of 3?
yeah,
You
it's
could.
the same thing multiplied by 2. So once
You
you be able
could.
to just add and or subtract 2/3, so it'd just be square root of 3i or
No,
square root of 3i.
okay, no, you can't do that, because the 2/3, this 2/3 is being multiplied by 1, and this 2/3 is being multiplied by something different, and so you can't combine those. Is that what you're saying? I'm not, okay, yeah. So you, if I understand what you're saying, the answer is no. Okay? Okay. All right, so let's look at maybe one more of these. Okay, one more. And this, we may not, this may have been mostly all, we may not get into the new stuff today, and that's fine, that's fine.
If we do one of these that's like, I know on the rule, there's one that's like, it'll be like -2x cubed. We're supposed to do something like this with that, I don't know how to do that.
Negative,
Yeah, or it'd be like 2x cubed, like the -18 or something, plus 18.
oh, yeah, well, that's what we just did. Look, that's what we just did. We had, yeah, we had that, right? We had, all you're gonna do in that case is you're gonna factor a 2 out. If you had 2x cubed minus 18, you're gonna factor a 2 out and get 2 times x cubed minus 9, for example, right? Those probably weren't the numbers, but I see what you're saying. Does that make sense? I'll show you after class, I'll show you. It's the same thing we just did. Okay, let's look at one more of these. How about one like this? Okay, first step is what?
Add 18.
Add 18, good. Okay, so we're gonna get negative,
Oh,
see, it's the glitch. Set it equal to 0, now what? Okay, multiply by -1, good idea. So 32x to the 4th minus 18 equals 0, now what? What we always want to try to do.
GCF?
GCF, so what is the GCF?
6.
No, it's 2.
2.
Yeah.
2, isn't it? Yeah. So I can undistribute a 2. Okay, this one's probably easy enough that we don't have to write them out as division problems. What's left behind if I factor out a 2?
16, x equals 4,
Okay,
and -9.
it goes to his bar.
okay, good,
How's it going?
okay. Thank you.
Chelsea, does 36 come to 32?
No.
Does not.
All right.
Okay. So now, I want you to notice something here. Here's another point that I can make that helps you simplify things just a little bit. So we know that by the properties of equality, we can always add, subtract, or multiply or divide both sides of an equation by the same number, and everything stays the same, right? I can't do that with a variable, that's different. But I could multiply, divide, add, subtract the same number to both sides, and everything stays hunky-dory, stays equal, right? What could I divide both sides by here that might be useful? 2, yeah. Now, if that was a 2x, I couldn't divide both sides by x, that's a problem, right? But I could divide both sides by 2 and cancel that 2. That's good, it makes things a little bit easier. Okay, now here's the next question. What's the factoring pattern that's gonna fit with that? That doesn't immediately look like a difference of squares or cubes.
Can you pull out a 2 cube?
And what do you think? Does one of those actually fit cubes? There's no way cube's gonna work.
No pattern, no
What do you
pattern.
think? Squares, yeah. Could we make this look like, there's the goal, could we make this look like a squared minus b squared, right? Because that's an easy one. That's just a plus b times a minus b, right? So the question is, can we make it look that way? Can we make this look like something squared minus something squared?
But 3 is.
Well, there's a 3. That one's pretty easy, right? But what about this one? Now, what squared is 16?
4.
4.
X
Okay, but what squared is x to the 4th?
X squared.
X squared. There you go.
Oh.
See the trick?
Yeah.
Okay, so if I ever have an x to the 4th in there and I need to fit that to a pattern, you can fit it into an x squared squared, can't you? It fits into the squared patterns. Okay, so then we know what this factoring pattern is. We're just going to get a, which is 4x squared, plus b, which is 3, times a, which is 4x squared, minus b, which is 3. And the whole thing is equal to 0, right? That's as far as I got to go, though, because now these are both factors that are squared. So if I set them equal to 0, I'm getting quadratic equations. They're easy ones to deal with, right? So we could just set 4x squared plus 3 equal to 0, or 4x squared minus 3 equals 0. Okay, so what are the steps to solve for x there? Subtract 3 and then,
Divide by 4.
so that's going to give me x squared equals negative 3/4. Now what? Or sorry, x to the 2, not x to the 4. Okay? Now what? Square root. Okay, so if I square root both sides, I get x equals plus or minus the square root of negative 3/4. Well, what's happening with that negative, first of all?
Turn it into an I.
That's an I. Right away, we know that's an I. Okay? So I get plus or minus something times I. Well, the square root of 3/4. That's just the square root of 3 over the square root of 4. What's the square root of 4?
2.
We got it. So that's just square root of 3 over 2, isn't it? Right? So I get plus or minus square root of 3 over 2i. There's 2 solutions. Notice they came as a pair. Whenever I get i's, they always come as a pair. And then over here, I get these other solutions. What are the steps to solve for x there?
Add 3, divide by 4.
So if I square root both sides, I get plus or minus.
Square root of 3 over 2.
Boom. Okay, we got it. Okay. So one last problem here. Let's just do, this will be a good place to end for the day. To kind of just get us a little glimpse into the next section. So this is one we've already done back in Unit 2. That's just a regular old factoring problem. If I'm going to factor this, what are my magic numbers?
Yes. 16 negative 1.
16 and negative 1. Easy, right? Okay? Now stare hard at that, at the top function, and compare it to that. It's almost the same. The only difference is that this, instead of an x squared, that's an x to the 4th, and instead of an x, that's an x squared. But the question is, could I make this thing fit the same pattern, right?
Yeah.
Well-
I guess what to-
Okay, so it's, in the last example, you know, we can fill in the blanks. We had something squared plus 15 times something minus 16 is what we were trying to factor, right? Now, the something that we started off with in the last problem
X.
was just an X in there, right? Okay, but it could have been a U, or it could have been a T, or it could have been a, whatever, a hand. It's just gonna fit the same factoring pattern. Whatever is inside there, we're gonna get that thing with our magic numbers. We got that thing plus 16 times that thing minus 1, didn't we? Right? So it was an X last time, but could it just be an X squared? Sure. Right? If it's an X squared, then whatever is being squared there goes there and there, right? And it's being taken to the first power there, which is fine. So I just use regular old magic numbers. Right? This is the exact same problem that we did back in Unit 2, only here we had packets of X. We had an X being squared and an X being multiplied by 15. In this case, we're doing the same process, but with packets of X squared instead of just a plain old X, right? So when we factor it, we get to here, right? Now notice that each of these factors, we may not be done. They each have an X squared, right? So this guy right here, this is something squared plus something squared, isn't it? Right? 16 is 4 squared. What's the pattern for a sum of squares? It's a trick.
There's no pattern.
There's no pattern, right? So this one doesn't, it's done. We can't factor that one any further because there's no pattern that fits. But this one right here, we could. This is X squared minus what squared? 1 is what squared? 1 squared, good. Okay. So then we can, this one we're stuck with, but this one we can break apart into X plus 1 times X minus 1. See what I'm saying?
Yes.
That's it. That's the next unit, is just, that's the trick. We'll look at another example tomorrow, then you can work, but essentially all it is it's taking the same trinomial factoring patterns we had in Unit 2, manipulating them to use packets of something other than X, and that's it.
Will you request
Yes.